at this point, we've done some review of like algebra concepts, and done a little bit of light geometry review. In chapter 2, we're going to be starting trigonometry in earnest. And our first order of business in trigonometry is we're going to take our definitions of sine, cosine, and tangent that are defined on acute angles in right triangles. We take that definition, we want to extend it so that we can take sine, cosine, tangent on all types of angles and no longer be stuck inside of a triangle. So that's going to be the goal here for chapter 2. Now the first two sections, the sections we're doing today, are going to be kind of building to that or towards that goal, but not kind of directly going towards that. But that's kind of where we're heading here in chapter 2. So we're going to reconceptualize what sine, cosine, and tangent mean so that we can apply those functions to angles of any size, no longer stuck between 0 and 90. Hey, what's up, guys?
Can you see if anyone's playing powder puff here really quick?
Yeah, go for it. Real quick, though.
No one.
Any puffers?
Okay. Thanks, guys. Thank you.
You're welcome. Good luck.
Thank you.
All right. So, in section 2.1, we're going to be talking about angles. So when we talk about the different ways to measure angles, we have good old reliable degrees. The measurement that we've used to measure our angles really since we got introduced to the concept of an angle, right? And then potentially a new one today, the radian. Now, there's other ways to measure angles too, like gradients or whatever. This is high school math class. We're not talking about any of those things. Radians will be the only other measurement we talk about other than degrees. Given that this is a new concept, let's start with just the general definition of what we mean or what a radian is. So the definition that we say is as follows. We say a central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. Mr. Kulik, I don't have any stinking clue what the heck you mean by that. Yeah, I know. That's okay. There's a lot of vocabulary in that, particularly geometry vocab. So let's kind of unpack this definition a little bit to give you an idea of conceptually what we're talking about. So I'm going to do that mostly with a picture and just kind of rehash some of this geometry vocab. So let's say we have some circle. This circle is centered at the point A. So when we talk about a central angle, let's use a color. A central angle, that's an angle whose vertex is the center of the circle, or of a circle. So in this case, CAB is a central angle. When we say intercepts, that means like intersects. So we notice that our angle, CAB, intersects the circle at points C and B. And we talk about an arc. Well, the arc that's intercepted is this arc CB. Does everybody feel okay there from a vocabulary standpoint? So what we're saying is that if the radius, so there's two radii that are written, either AB or AC. So if we can say the measure of AB is equal to the measure of the arc CB, then the measure of angle CAB is 1 radian. So that's kind of what the definition is saying. That if the radius and the intercepted arc have the same measure, then that angle has a measure of 1 radian. Cool? It's all right. So now we have these two different measurements. We have degrees and radians. As soon as you get two different measurements for the same object, what do you want to have? So let's say you have like feet and centimeters. What do you want to have if you have two ways of measuring something like feet and centimeters? Just from a practical standpoint, what do you need to have? Well, not necessarily inches. You don't need a third measurement to go in between them. But what would you want to have if you have two ways to measure the same thing? Not congruency necessarily. You want a conversion factor. You want a way to take feet and turn it into centimeters, or a way to take degrees and turn it into radians. Because probably most of us have a good intuition about what like a 45-degree angle looks like, but nobody has really any idea of like how many degrees is like a 1 radian angle. I don't know. What is that? Be nice to have that so we can start developing some kind of intuition about like, is that a big angle or a small angle? Right? Is everybody okay with that idea? All right. So let's do that next. So what we were looking for is to find a conversion factor between these. So when I say conversion factor, I mean something like, we know that there's 2.54 centimeters in 1 inch, or 12 inches in a foot, or, 1,000, meters in a kilometer, something like that. Those are what we mean by conversion factor. So to do this, I'm going to start with a picture, kind of use that picture to construct our conversion factor. So if we take a look at this picture, I see that we have a central angle, which is angle CAB. And what's the measure of that angle CAB in degrees? Who's taking a risk? Jake, I saw you hesitate. Yeah, that's good. So it's labeled on the picture, but you might also have just figured it out by looking at it and seeing that it's half of the circle or that it's a straight line, right? Any of those would be reasonable explanations. Everybody's happy there? Okay. And then we have our arc, CB. What does the measure of that arc, CB, have to be? Well, sometimes you measured arcs with angles or with degrees in geometry. I'm talking about the arc length, though. How, like the distance that it would be traveling from point C to point B. Miriam? Not quite that, but how much of a circle how much of a circumference is CB? Right. It's half, right? Half of a circumference?
Yeah. Isn't the radius half?
And a circumference is 2 pi r, right? So CB would just be pi r.
Yeah, that's right. That's what I was trying to say because I thought the R would be like 90, which is 180, but I forgot it's
R is a distance, right? Not an angle. That's okay. So everybody so far so good? Okay. So we have this, right? So what I want to do now is I want to try to figure out, okay, we know CAB is 180 degrees. I want to figure out what that is in radians then. So I remember that if I had, in my definition above, we have that if the radius is equal to the arc length, then we have 1 radian, right? So our radius is r. So if I make something an angle like that, that's 1 radian there, right? Everybody's agree with that? Because the arc length and the radius are the same distance. How many of those little slices can I make? How many of those little slices can I make? Can make pi of them because their arc is pi times r. So I can have pi slices of r, right? Is everybody okay with that? So I have pi 1 radian angle slices. Yes?
How do you know what the distance of each one?
When I drew the picture,
Yeah.
I just labeled it as r.
Oh.
I just drew it so that so each arc was r long. Obviously, they don't look like they're the same distance because they don't, but that's okay? Okay. So here's the takeaway, right? So we can slice this angle CAB into pi 1 radian slices, which tells us the measure of angle CAB would be pi radians. So CAB is 180 degrees, and it's also pi radians. There's my conversion factor. Is that pi radians is 180 degrees, or 180 degrees is pi radians. That's my conversion factor. That's what I was looking for. So like, if I have some angle measure in degrees, and I want to convert it to an angle measure in radians, I would need to multiply that by pi over 180. If I want to go from an angle measure in radians to an angle measure in degrees, I have to multiply that by 180 over pi radians. So this is probably the way that's more useful to us on kind of thinking about that conversion factor, right? Those of you that have done like a chemistry class or probably almost any science class have done unit conversions at some point. And this kind of a diagram probably looks pretty familiar. When converting from one unit to another, we draw these kinds of things and label the conversion factors going one way versus the other way, right? Maybe something, signs of life. Let's do some examples. Make sure that this is clear. All right. So we're asked to convert 90 degrees to radians. So 90 degrees, we're going to multiply that by something so that we have an answer in radians. Everybody feel okay so far? What do I need to multiply 90 degrees by to convert it into radians? Well, I'm starting here at an angle in degrees, and I want to go to an angle in radians. So what conversion factor do I need? Pi over 180. So when I multiply these, the units cancel, degrees cancels with degrees, and we're left with only radians. So I know I have an answer in radians, right? Now, in trigonometry, the convention here is, if possible, we want to write our radian measure in terms of pi. So if I look at this, I'm going to just try to reduce the 90 and 180. What is the common divisor between 90 and 180? What? 90 is correct. You know, just shout them out. It's okay. So when I divide 90 by 90, I get 1. When I divide 90 or 180 by 90, I get 2. So what am I left with? I have 1 times pi over 2, or just pi over 2. Everybody okay here? I want to point out to you that if I wanted to do that reducing of fractions on the calculator can handle that. If I just want to do 90 divided by 180 on my calculator, and then I press the math button and select the fraction command, and then press enter, it tells me that that is 1/2. So I just stick the pi on top of that and I'm done, right? Everybody's okay there? Alternatively, like there's no reason I couldn't give this a decimal answer. So if I took pi and divided it by 2, I get the number about 1.57. Why do you think that in mathematics we prefer the pi over 2 answer to the 1.57 answer? Miriam. How so?
Because it shows that like pi is over 2, but if we just look at the bottom, we're just considering decimal.
Okay. We're getting close. When I wrote down this 1.57 number, was that the entire number? It was a long decimal. What did I do there to write down 1.57? I rounded. Did we do any rounding for the pi over 2? No. So if possible, we like to give an unrounded answer. That's why We prefer the ones in terms of pi to the decimal. Are they the same answer? Yeah. But we would rather have the unrounded answer than the rounded answer. Everybody okay with the reasoning there? Okay. Let's do the next one. We want to convert 152 degrees to radians. Okay. So if I want to convert 152 degrees to radians, what do I need to multiply it by? Over? Yes. It's the same problem, right? Taking degrees to radians, the conversion factor will be the same. So the degrees cancel. And then if I want to reduce 152 over 180, I'm going to look for a common divisor between the two. Does anyone see a common divisor between 152 and 180? 2. Well, let's start there because that's easy to see, right? Past that maybe is kind of tough. 150 divided by 2 is going to be 76. 180 divided by 2 is 90. Now, if I look at 176 and 90, do we see a common divisor there? What? 2 again. How can you tell that 2 works again? They're both even. So that's going to be 38 and then 45. Do we see a common divisor between 38 and 45? The only prime divisors of 45 are 3 and 5. Obviously, 5 doesn't divide 38 because it doesn't end in 5 or 0. And I know 3 doesn't divide 38 because the sum of the digits 3 plus 8 isn't divisible by 3. That's a trick for telling if a number is divisible by 3. If you add up all its digits and that number is divisible by 3, then the whole number was divisible by 3. So we're done here. So we'll just call that 38 pi over 45. And again, this one would have been a good candidate to use your calculator to do the reducing. If I just do 152 divided by 180 and I do math, fraction, and then enter, there's my 38 over 45. All I have to do is tack the pi on. Everybody's okay? If I include the pi, will the calculator do this? No, because if there's a pi in there, it can't write it as a fraction because it's not going to be, because pi is irrational. Can't take an irrational number, turn into a fraction. So you have to leave the pi off and then put it in yourself at the end. And if I wanted to turn this into a decimal, depending on the directions, they might ask for a decimal answer. I can just type in 38 pi divided by 45, and we'll say that's about 266. How did I add the pi on? I pressed second and the number or the caret symbol here. See above it in blue is the pi symbol. Is that what you wanted? Okay, cool. Just making sure. And then our next one says we want to convert 2 pi over 5 radians into some number of degrees. What do I need to multiply 2 pi over 5 radians in order to convert that into degrees? So if I go back and I look, 180 over pi. So the units of radians cancel. And I have a pi that'll cancel. And now I just need to do 2/5 times 180. I'm going to do that by looking at 5 and 180 and look for a common divisor. What's the common divisor between pi and 180? Between 5 and 180. 5, right? So 5 divided by 5 is 1. 180 divided by 5 is 36. And then I have what's left here, 2 times 36 degrees, or 72 degrees. Degrees, we always just write as a number with a decimal. We don't ever worry about in terms of pies. So I'm just going to leave that as 72, and that's all there is to it. I have one more example. So here we have 1.5 radians times something to give me some number of degrees. What do I have to multiply 1.6 radians by? 180 over pi. So again, the unit cancels, radians and radians. But notice the 1.6 doesn't have a pi attached to it, so I can't cancel that pi out. At this point, I think it's just calculator time, right? So I'll do 1.6 times 180 divided by pi. And there's my answer, about 9167. I'll turn that into squiggles to show that I did some rounding there. Everybody feel okay doing this? Pretty easy, right? NBD. That stands for no big deal.
You just said 1.6 times 180.
Divide by pi. All right. One of the things you probably talked about in your geometry class, but maybe you don't remember, is how to calculate an arc length on a circle. So in geometry, we said S is equal to your central angle measure in degrees divided by 360 times the circumference of your circle.
Is it 91.67 or 9?
Oh, yeah, 91. Thank you. I missed the number there, huh? Thanks.
What is this? Top of the direction.
That's the symbol theta with the subscript d on it, meaning that it's an angle measure. That's the central angle measure in degrees.
Okay.
So the d is for degrees. Yes. Absolutely. So if I notice here, I can kind of reduce, right? I have the 1, 360, and the 2 can reduce. And if I rearrange this a little bit, I can write this as that theta d times pi over 180 times r. What do I get when I take an angle measure in degrees and multiply it by pi over 180? What do I get when I take an angle measured in degrees and multiply it by pi over 180? An angle measured in radians. That's exactly right. So that's a lovely improvement, right? We went from this big complicated formula down to just the angle measured in radians times r. Let's make that a definition. So we say that if the central angle theta measured in radians of a circle with radius r, then the length of the intercepted arc is given by s equal r times theta. And just as a reminder, that formula was based on that simpler, or that other form, this formula from geometry where here our theta is in degrees. When I write these, I always put a little subscript on my theta on problems where it could be radians or degrees, just to remind myself like which one I like to use, right? So like I put a little r on the bottom of this theta. I put a little d at the bottom of that theta to remind myself that that's an angle in radians and an angle in degrees. You don't have to do that, but I like to. Just reminds me. Let's practice using this formula now. So we practice doing conversions between radians and degrees. Now let's practice calculating some arc lengths. So the example A says solve for S if r equals 1.5 meters and theta equals 0.98 radians. Hi, Miss Yarrow.
Hi, Mr. Kurikow.
Excellent. What can I do for you?
Can I have you for a moment?
Me?
You.
Oh,
I
my.
need to confirm something with you before I act on things.
Sure.
Because, you know, I hear stories and then.
Yeah, we're not here. I know, I'm not. I'll go back and look at it the day before. Just you. Let's go.
Hi. Where do we leave off here? Okay. So what the first thing I need to look at is what measurement is my angle in. In part A, the measurement is radians. So I need to use that formula. So all I have to do is plug it in and type it into my calculator. Is this some easy stuff right now? Mr. Cool, all I'm doing is like picking the right formula and then plugging the numbers in? Yeah, dude. So I have 1.372. And what unit should this have attached to it? This is S stands for the arc length. So it should have a unit of distance attached to it. What unit of distance should this one have? It should match whatever the radius is, meters in this case. Is everybody okay with how I figured all that out? Let's do the next one.
Mr.
Yes.
For like quizzes or tests, will we have the formulas or?
Well, you have a note card,
Oh,
right?
okay.
So either way, you could have it if you wanted, or you could memorize it, whatever you want to do. How's that sound? Yeah, I think it's okay. All right, let's look at part B. Here it says solve for S if R is 3.8 inches and theta is 40 degrees. First thing I do is look at how the angle is measured. In this case, it's degrees. So I'm going to use my other formula. So we just fill in now. The radius is 3.8. Theta is 40 over 180. And now it's just calculator time for my dude. So I'll do pi times 3.8 times 40 divided by 180. So 265-ish. And what unit should this be measured in? Inches, because that's what the radius was measured in. So far, so good. Next one says solve for R if S is 18 centimeters and theta is 2.13 radians. First thing I do is check to see how the angle is measured. In this case, it's in radians. Oops. Stick with my color coding. Now, in this case, we're given S and theta and asked to solve for R. Everybody's cool? How do I get R by itself? I just divide, guys. Is everybody all the way asleep? You're here. That's one. You got one awake. It's not great. Not great, Bob. So 18 divided by 213 is 845-ish. And the unit here should be centimeters. What do you think? So far, so good? Yeah.
How do we know like what formula to use?
It's all dependent on how the angle is measured. If it's in radians, I need the radian formula. If it's in degrees, I need the degree formula.
And on this C problem, what's the little letter that?
That's an R. This subscript, that's an R. Does it really look like a D? I'll draw it, make it maybe a little clearer. Yes, sir. Absolutely.
So what's like BR?
The central angle measure.
Okay.
Right?
So it's just like every
Because what you're talking about here is you have a picture, right, where that's R, that's theta, and that's S.
Okay.
Does that help to remind us what these letters stand for? Pictures I like. I'm a pictures guy. Okay. Let's look at another example problem here. This one's a little bit more, I don't know, a little different. It says, find the perimeter of a sector with a central angle of 1.7 radians, cut from a circle with a radius of 5 centimeters. What word in here is the one that's the problem? What's the word in here that we're like, what the heck does that word mean? Sector, yeah. That's a geometry term that we probably don't remember. What is a sector? A sector is a slice of pizza. So this guy here, slice of pizza, is our sector. What does perimeter mean? Just in your own words. The distance around, right? So that side is R because it's a radius. That side is R because it's radius. And that side is S because it's the arc length. So our perimeter here should be R plus S. Everybody feel okay with that? Well, we know what R is, right? That's just 5. And since we're given a central angle, and we see that that's in radians, I should be no problem calculating S So my perimeter should just be 5 plus 5 plus 8.5, or 18.5. And the unit there should be in centimeters. Yep. What you guys think on that one? It's all right? It's all right, Mr. Kulik. Yeah, sight. Great way of phrasing it. One more example for this section. We'll move on to the next one. This is probably the trickiest one for most students. So it says a car has 18-inch diameter tires on it. And it says if a car is traveling at 15 miles per hour, how many revolutions per second are the tires making? Ooh. This is just a unit conversions problem, though, where we're asked to go from miles per hour to revolutions per second. Okay, whatever, fine. So we know we're starting with miles per hour, so I know I have 15 miles in 1 hour, right? If we're going 15 miles per hour. And I want to end in revolutions per second. Well, the hours to second should be easy, right? Because I know that 1 hour is 60 minutes. And 1 minute is 60 seconds. So when I multiply these, the hours cancel with hours and minutes cancel with minutes. And now we're in miles per second. So we've done that part. We still need to do the miles to revolutions piece, though. So here's my question for you. How far is 1 revolution of a wheel? How far is 1 revolution of a wheel? So you have some wheel, right? Sits on the ground. You know, it starts turning that direction. It ends up in the new spot. How far did it go? What do you guys think? All right, let's think about it this way then. This one spot right here in blue is touching the ground on the wheel, right? How many spots touched the ground as it went to the same spot there? How many spots on the wheel touched the ground on the way from the start to the end? Well, all of them, right?
Yeah.
So if every one of those points on the exterior of the circle touch the ground, then one revolution is just one circumference, right? That's our key. In our case, what is the circumference? 2 pi r, and r in this case is what distance or length? 18 inches is the diameter, so the radius, the r, is 9. That's okay. That's okay. So I know that one revolution in this problem is 18 inches. But this is kind of the key idea for any kind of these type of problems where you're going from a linear to a rotational conversion, is that one circumference is one revolution. So I notice that my circumference is in inches. So for me to do this, I need to convert then miles to inches before I can apply that final conversion factor. Well, I don't know how many miles or how many inches there are in 1 mile, but I know 1 mile is 5,280 feet. And I know 1 foot is 12 inches. And then I can say that 18 pi inches is 1 revolution. So if I cancel these units, now miles cancels with miles, feet with feet, inches with inches, and we're left then with revolutions per second. So all I need to do is to type this into my calculator now. So I'm going to use that fraction command and do this all in one line. So I'm going to do alpha y equals and pick that first option. So in the numerator, I have 15 times 1 times 1 times 5,280 times 12 times 1. I'm not going to bother with any of the ones because I know when I multiply by 1, it doesn't really do anything. And then the denominator, I have 1 times 60 times 60 times 1 times 1 times 18 pi. Again, I'm not going to bother with any of the ones. And then I'm going to press enter. So I have about 467. And we're in revolutions per second. What does that mean? When your car's going 15 miles per hour, the wheel is turning 4 2/3 of a time every second, right? That's what we're saying. Everybody's cool? Sweet, Mr. Kulik. I know. All right, that's it for 2-1. 2-2. We're going to look at these trigonometric functions on acute angles. Yes, sir. No problem. So if we think back to our stuff we talked about the other day. We know that sine, cosine, and tangent are defined inside of a right triangle. So here's my right triangle. There's my acute angle theta, and I've labeled the sides opposite, adjacent, hypotenuse. From SOHCAHTOA, I remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, right? Did you notice, though, that there's some other ratios that we could write that don't correspond to a trig function, right? Why isn't there hypotenuse over opposite or adjacent over opposite, right? Why not have those? Why didn't we define a function for those things? Guess what? There is functions for those things. We just didn't tell you about them in geometry. We're going to do that right now. So there's actually 6 trig functions, because there's 6 ways to write these ratios. So these 3 new ones, the first one's called cosecant, which we abbreviate as CSC. And then there's secant, which we abbreviate as SEC. And then cotangent, which we abbreviate as COT. Did you notice anything about the relationship, say, between sine and cosecant? Did you notice anything about the relationship between sine and cosecant? One is opposite over hypotenuse. The other is hypotenuse over opposite. What do we call that relationship? Those 2 fractions are, starts with an R, reciprocals, yeah, where one fraction is just the flip of the other. So rather than memorizing a new set of trig functions, what I'm just going to do is I'm going to remember that sine and cosecant go together, and they're just reciprocals. So if sine is opposite over hypotenuse, cosecant is its reciprocal, hypotenuse over opposite. Similarly with cosine and secant, and tangent and cotangent. They're just reciprocal pairs. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. So I'm not memorizing a new set of identity or a new set of definitions. I'm just going to remember which ones are the reciprocal pairs of the definitions I already know. Now, tangent and cotangent, easy to remember, those 2 are a pair, right? Keeping straight sine with cosecant, cosine with secant is the tricky one. What I remember is just that cos don't go together. So cosine doesn't go with cosecant. It goes with secant, right? The cos don't go together. Everybody's okay? Okay. That's the sole new idea for today. Let's look at some examples where we use some of these new trig functions. So it says here, find the exact value for all 6 trig ratios for theta in the right triangle. Okay. Well, I'm going to need to do sine theta, need to do cosine theta, do tangent theta, and I'll have to do cosecant theta, and I'll have to do secant theta, and I'll have to do cotangent theta. Okay, let's just start with sine. How do I do sine? From SOHCAHTOA? Thank you. Woof, that was such a delay. Opposite over hypotenuse. And what is the opposite in this case? No, what is the opposite? What number? Number from the picture. 5. What's hypotenuse? Okay. What do we do then? Great. So we can find that missing hypotenuse using the Pythagorean theorem. 2 squared is 4. 5 squared is 25. 4 plus 25 is 29. And then we'll square root both sides. What's the one thing we have to be careful about with the Pythagorean theorem? Not to square root the whole thing, but I think even more common is make sure the hypotenuse is the piece that's by itself. The hypotenuse is the c squared, right? Don't forget that. Okay. So sine then should be 5 over the square root of 29. How's that answer look to you guys? We're not going to leave it that way though, right? What's wrong with it? Square root in the denominator. Yeah, how do we get rid of that? Yeah, and when you say both sides, you mean the top and bottom by the square root of 29. So if I do 5 times the square root of 29, that just is 5 square roots 29. What's square root 29 times square root 29? Regular old 29. Excellent. So there's my sine. What's cosecant going to be then? Go ahead. No? Sine and cosecant are reciprocals. So we'll just do that. Why didn't I take the final answer and flip that one? Kate? Because I moved it around, and why? What would be the why? Okay, so I did, but why is that a problem if I flip it now?
You would have to multiply by 29.
Yeah, I would have to redo that and multiply by the conjugate thing till I get the square root out of it, and I have fractions to reduce. It's like a whole mess. Just start with the original, right? You know what I'm saying? All right, cosine's up next. How do I do cosine? Great. And what's the adjacent in this case? 2. And what's the hypotenuse? Square root of 29. Thank you. And again, what do we have to do here? Yeah, multiply top and bottom by square root 29. So 2 times square root 29 is just 2 square roots 29. Square root 29 times square root 29 is just 29. What's secant going to be then? Who can tell me? Secant. It's the reciprocal of cosine. So it should be square root of 29 over 2. Right, I just take the answer for cosine before I messed around with it and flip it. Flip it for real. What's tangent going to be? Over adjacent. And what is opposite? And adjacent. So what's cotangent? 2 over 5. What do you guys think on this? NBD, right? Same stuff as what you did in the delta maths. Oh no, I have 3 new things to do, but like, whatever, just the reciprocal of the answer you got from one of the other 3 things that you already done. You know, it's like, all right, whatever, no big deal. What if we ask you a question this way? Let theta be an acute angle of a right triangle. If sine theta is 1/3, find the values of the other 5 trig ratios for theta. What should I do first? Dude, I'm drawing a picture, right? There's my right triangle. Call this guy theta. Since sine theta is opposite over hypotenuse, opposite is 1, hypotenuse is 3. How am I going to find that adjacent side?
1x squared plus x squared.
Pythagorean theorem. 1 squared is 1, 3 squared is 9, 9 minus 1 is 8. We square root both sides. Can I simplify the square root of 8? You betcha! Right? 8 is 4 times 2, so the square root of 8 is the square root of 4, which is just 2 times the square root of 2. Is everybody okay? If I went too fast or you're not sure, please stop me and say something. So sine theta, I'll write that in black because that's a given thing. We know is that. We still need cosine theta, tan theta, and then cosecant theta, and secant theta, and cotangent theta. Well, let's start with cosecant. What's that got to be? 3 over 1 or just 3, right? If you write 3 over 1, that's fine, but like, why? Right? Let's make it 3. What's cosine going to be? Just the numbers, guys. Two root 2 over 3. That looks great. Adjacent over hypotenuse. What's secant going to be then? Yeah, 3 over 2 root 2. But is that okay? No. All right. What are we going to multiply it by? Just do root 2 over 2. It's fine to do 2 root 2 over 2, but then you have extra reducing to do at the end. Guaranteed. If you do just the root part, that'll be fine. So when I multiply root 2 times root 2, what do I get? 2. And then so I have 2 times 2, so that's 4. Feel good? What's cosine going to be? Just, the numbers. One over 2 root 2, right? Opposite over adjacent. And we got to do that same thing to the denominator again. So root 2 over 4. What's cotangent going to be then? I would flip this one, because then I don't have any denominator to rationalize, right? Not wrong to do it what you're doing, but it's going to be longer. And like, I'm just in a hurry in general in life. Like, I don't want to do it the long way. Give me the easy way. Stop messing around. Don't pull my chain, man. I don't want to mess around with the long way. Let's get this done. It's football season. There's probably some kind of game to watch or fantasy lineup to set. All right. So here we're saying find sine 30 without using your calculator. What's the catch here? The hard part about this problem? What makes this problem hard? Yeah, without using your calculator. Okay, fine. Well, let's start by drawing a picture. I don't know what else to do here. So here's my right triangle. Here's 30 degrees. What's the other angle have to be? 60. Oh, 30, 60, 90 triangle. That was a thing, right, from geometry? that has known side lengths that are in ratio x for the short side, x root 3 for the medium side, and 2x for the long side. So sine 30 then should be opposite over hypotenuse. The x's reduce out, and that just turns into 1/2. Was there another special right triangle from geometry? Well, I'm guessing there is, Mr. Kulik, because you've already started drawing a triangle. Way to give it away. Of course there is. It's the 45, 45, 90 triangle with side length ratios x, x, and then x root 2. You should take a moment to memorize those special right triangles, or at minimum, do what with them? Put them on your note card. You will use these a lot here in the next coming sections. So they're going to come up a bunch of times over and over and over again. They're nice ones to know. Okay. Let's do this next then. Oops, that did not happen where I wanted it to. What if I ask you to find sine of 17 and secant of 78? Notice what is missing from the direction on these problems. Doesn't say you can't use your calculator. So what am I going to do? I'm going to use my calculator. Well, sine 17, that's like easy, right? Just type in sine 17. Oh, what do I need to check, though, before I press enter? I got to check my mode, make sure I'm in degree mode. Now, I use my calculator all the time for a bunch of different classes, so I'm switching back and forth all the time. Most of you guys are probably, once you've set it to one thing, it's just going to stay there for you. But you should check that periodically, especially if you can't get the right answer, right? So sine 17 is about, 0.293. Oh, no, 292. Everybody's cool with that? But how do I do secant 78? I don't see a secant button anywhere here. Well, remember, secant is the reciprocal of which trig function? Cosine is right. So what I'm going to do, instead of doing secant 78, I'm going to do 1 over cosine 78. And that'll be the value for secant of 78. Because secant and cosine are reciprocals. So I have what? 4.81. 0 if you want the third decimal place. I don't know if you care. Everybody's cool? No big deal, right? So that's how you do like cosecant or tangent or whatever similarly, right? Just 1 over sine or 1 over tangent or 1 over... Okay. That's it for today. That finishes her up for section 1 and 2. At this point, you guys should be able to do up through 42. You were looking at that going, oh my goodness, Mr. Kulik, are you kidding me? I would say half of those problems are either converting from degrees to radians or typing the number into your calculator for like secant of 78, pressing enter. So like literally half the problem are like 10-second problems. So like there's like legit maybe 20 of those are real problems and the other 20 are like, like, okay, that's 3 minutes worth of calculator punching and then pressing enter problems. So it's not as bad as it looks. Keep in mind when you're doing this, if you're getting the wrong answer consistently, what is likely the issue? Mode on your calculator. Make sure you're in degree mode or radian mode depending on the problem. Okay? If you don't do sine or cosine in the problem, does it matter the mode? No. So if all you're doing is like things without sine, cosine, or tangent, the mode of your calculator does not matter. Degree or radian, who cares? They'll all do it the same. If you're doing anything with a sine, cosine, or tangent, though, you have to be careful. Cool? Okie dokie. That's it for me for today. So you guys got what? Like, oh boy, we took a long time.